think I passed back all the papers I have for y'all.
None of them? That's annoying. You're good. They should be
Okay.
on the side, yeah.
So, please make sure, again, you have these pages cut out, or torn out, cut out. We're going to use all of those. I will say this, just as a quick note, for what I had noticed in the past was most students did not want to hold on to a textbook. If you would prefer to just hold on to a textbook and just cut pages out when you need to cut them out, you can. But I also know there's only so much room in our backpack and we are not going to use every lesson from the book. But just be aware, if you want to do that, you can. Alright, how do you know if it's linear, exponential, and quadratic doing the table? So, anyone have a strategy, because there's two major strategies I can think of when identifying linear, exponential, and quadratic with the table. Does anyone remember any of those strategies? So looking at the rate of change. The number one strategy that I recommend is by looking at the rate of change. However, if you're struggling with the rate of change, what else could you do? Say again? You can always graph it as well. So don't forget, it doesn't matter which representation you're looking at, it should tell, or will tell, the same story.
So one more. Actually, one more for that.
So like here, -3, -1, +1, +3. So every time it's constant additive here. And so if it's a constant additive here, this rate of change is linear additive, right? A linear function has a constant additive rate of change. And so if we get to a constant at the second level, what is to the left of that is going to be that linear additive, okay? And if I were to take the time to graph this,
You know,
-3, 4, -2, 1, 0, or -1, 0, 0, 1, and 1, 4. Notice how it creates a parabola, right? So quadratic, rate of change, or graph it. Same thing with the rest of these. Rate of change, which remember you do want to always look at the change in x because it needs to be additive almost no matter what on the left-hand side for now. And so because that's constant additive for both the change in y and change in x, it's going to be linear. I graph it, and it's going to be linear. Now, sometimes exponential can be a little bit trickier, depending on how it's set up. So for example, let's go 54 there, 36, 24 I think, 16 and 32/3. So when I look at this one, I'm always going to look for additive first. And minus something. Now granted, I will point out this fraction here is a pretty big hint that we're probably going to have what? A constant what? Say again. Say again. A multiplicative rate of change, but what's that name of that multiplicative rate of change? A constant factor, right? So a constant factor here. In fact, my guess would be 16 times what gives me 32? 16 times 2, right? And I'm just dividing by 3. Probably my constant factor. Just thinking logically, so same thing though. If I take 54, by the way, it was not constant additive or even linear additive if you were to check. 54 times f would equal 36. If you solve for f and type that into a calculator, don't forget you've got calculators, that factor comes out to be 2/3. So rate of change is the best one, is the most effective one I will say, but you can always take the time to graph. Does that answer our questions, group of 8? Okay. Any more? As a quick recap. All right. So agenda for today, we're going to do a textbook lesson on the forms of quadratics to build off of what we did with Desmos. Hopefully you did check your understanding on those different forms of quadratics that will help you significantly today, and then get into writing quadratic equations. So we're going to start with Mathematician Monday, and we're trying to move through this a little bit quicker, not because it's bad, but we got to get to math and honor that mathematician. But today and the rest of this unit is all about connecting forms of quadratic equations with features of the graph. By the way, what's the graph of a quadratic called again? Say it loud. A graph. What's this thing called? A parabola, right? Okay. So don't forget, it's a parabola. So Mathematician Monday. So I realized, I don't know how I didn't notice this earlier, but I don't think I've done a single female mathematician, and so I wanted to fix that, right? So Dr. Erica Tatiana Camacho, I think is how you pronounce her name, was born in 1935 in Guadalajara, Mexico. And so one of the things I hope you're starting to see is anybody and everybody, it does not matter your background, can be a mathematician. She was born in Mexico. Her family had next to no money. Her dad died when she was 3 years old, and she actually had 3 older siblings. And her mom was trying to raise them on their own, and it was a struggle. In fact, they went and lived with their grandmother for a little while, and then their mom had to take them back because the kids hid it, but the mom eventually realized that the grandmother was forcing them to go out and sell candy and sell all these things to raise money. None of the money that the mom was sending to her kids was actually making it to the kids, right? And so like that's the experience that they grew up with in Mexico. They moved to America, I think when she was 13 or, no, it had to be before 13. Maybe it was 8 or 10, somewhere in there. But they moved to America for the mom's fiance. The fiance had promised that he had actually more money than he did, and so they ended up having to move in with his adult nephew. Wild situation. Obviously, moving from Mexico, they did not know a lot of Spanish. They moved into an American or an English-speaking area, dealt with racism and bigotry very heavily. And this is where I really want to focus on her story is East LA. So a year or two in, they moved to East LA. And in 7th grade, she was mistakenly placed in an honors English class rather than an ESL, right? English as a second language class. So she's a couple years into living in America, does not know English very well, and she was placed in an honors English class. And they tried for a week or so to get her out of that class, and basically the guidance counselor said, sorry, too bad, like that's where you're placed, and we're struggling to get people placed in the right spot. I think there was something like 100 students that were not placed at all yet. And so the teacher ended up deciding, hey look, if you'll come in during lunch, if you'll come in after school and come through the tutoring, and if you work hard for me, we'll make sure that you make it through this and that you learn. And then after that, she was in honors English for the rest of her career in high school. Okay? So it's one of those things that like, this is a phenomenal story to me because like math, there's like a universal component to math. It's still hard to learn when it's not your native language, but to go from not knowing English to surviving in an honors English class, like that just speaks to the power of hard work and support and overcoming that struggle. And so it's one of those things like, I don't think she's special because of it, but I think that she became special because she overcame that struggle. And so I want to encourage you to always take on that struggle, take on that burden, and overcome it, right? In high school, she had a teacher named, and I'm going to tell you, I should have looked up how to pronounce his name. I'm assuming it's Jamie Escalante, but he's from Bolivia. There's a movie from 1988, I did look that up, called Stand and Deliver. And like this guy was such a big deal that they made a movie about the impact that he was making in his Hispanic students' lives. And so one of the things that she said, and still resonates with me, and this is the experience that I had in high school, and so I would never say that I'm the smartest person ever, not even close, but I was challenged all the time to be better. And so the tough love and that challenging support is what helped his students go beyond. He regularly pulled students in who had like alumni who had gone on to places like MIT. And so she, I don't remember exactly what she wanted to do, but I think she had a dream of being like a store clerk was her dream. And somebody came in from MIT and was talking about the engineering that he was doing at MIT, and she had a new dream, okay? And so I want to encourage you that difficulty is not bad, difficulty is how we get better, by overcoming and working hard and things like that. And so both her in her English and in her mathematics shows this. She struggled with racism all the way through her PhD. She struggled with it even in her very first career, or her very first job as a professor. But she got to do cool stuff. She now studies mathematical physiology. And so literally, blindness is a major issue for people, going blind eventually. And so she was the very first one who went from, let's not look at it just as a scientific lens, but let's look at it mathematically. What is happening there? And so there's mathematical structures always at play underlying a lot of phenomenon that we don't get to see. And so she said, let's look at what's happening mathematically. I think she has like 20 plus publications, which is really hard to do in top tier journals looking at the mathematics behind that. And so the challenge I want to extend to you is, what difference are you going to make? Right? She overcame those struggles to start examining a new way of thinking about mathematical physiology and blindness. And I'm not saying that that's what you have to go on to, but I am saying, like, what's your drive? What difference are you going to make in this world? How are you going to impact the world around you? And it can be simple things, it can be big things, but I just want to challenge you to overcome any struggles that you're thinking about, any struggles that you currently have, and what difference are you going to make. So that's Dr. Erica Tatiana Camacho. Again, really cool history if you want to look at it more heavily. But now, on to the mathematics. That was her foundation to being successful. And yes, I know, like, she took classes in the 60s and 70s, and the math has not changed. There's beauty to that. There's consistency, patterns of relationships. Maybe the way that we learn it has changed a little bit, but that's because we are learning better and better every year how to teach math more effectively for that strong conceptual understanding before just doing procedures. All right, so we're all about functions with linear additive rates of change called what again? Well, what type of function has that linear additive rate of change? A quadratic, right? So remember now, when we say factor, what does that word factor mean? To what? To multiply, right? Which is why that exponential has that constant factor. We did have a factored form of a quadratic. Anyone remember what that factored form was? Okay, let me write the three forms up here. I'm just going to write the three forms. Alright, do you think that's my factored form? Okay. Anybody want to add on to or push back? That's what? You thought that was vertex? Okay, if that's vertex form, which part is the vertex? Which part of this is my vertex? Well, let's look here. So this is vertex form. Which part is my vertex? Was it H or is it K?
H is the X value, and K is the Y.
Oh, X value the vertex and the Y value the vertex. Do not forget vertex, X-intercept, Y-intercept. Those are all points. You got to have both an X and a Y. Okay? What are R1 and R2? Close. Very close. They're part of the X-intercepts. Does anyone remember why we use R1 and R2? What that stands for? It's a key word. The roots. Remember, R1 and R2 are the roots. If I want to turn them into an X-intercept, though, what's the X-intercepts? Well, this is a good thing I'm doing this quick little review here. Hey guys, what do you know about every x-intercept that's ever existed? The y is what?
0.
Okay, so what's the x value? Whatever r1 is, comma, 0. And what's my other x-intercept? r2, comma, 0. Okay. So there's our roots. And then so which form is this one up top? Standard form, right? Remember, each form has a different piece that it clearly identifies, right? Obviously, factored form. By the way, why do we call that factored form? Not because we can distribute. Why do we call it factored form? It's just as it is right now. What are we doing? Oh yeah, we're doing what? We're multiplying two linear factors, right? Called factored form because it has factors. It's in the name. It's factored form because it has what? Factors, right? All right, there we go. So factored form because it has factors. Just like this is called vertex form because it has a vertex. And the top one is called standard form because, well, that's the standard form of every polynomial that we'll study. At least that's how I've always understood it. Is that fair to say?
Yeah, that's something fair to say.
Yeah. All right, so those are those different forms. Each form has a different feature, but I will remind you, can I find a vertex from the factored form?
Yes.
Does anyone remember how I can find that vertex?
Yeah. B minus.
Now, say that one more time.
B minus B over T times, well, divided by T times A.
Okay. I want y'all to look again at that equation. Where do you see B and A in factored form? You don't. So think about that again. Where's negative B, or the opposite of B divided by 2A going to come up? That's for standard form. Notice how I even labeled it as H, right? H equals the opposite of B divided by 2A. But does anyone remember where H was in respect to my roots, maybe? And so you can memorize that equation, sure, but what does that really mean? What are we really doing there? Landon kind of noticed this, which I know he's not here right now, but Landon kind of noticed this intuitively, which he does, what I like to call it, mathematician magic, but that's not the word I use. But he uses math magic to just kind of see things sometimes. But where's R1 plus R2 divided by 2 coming from? What are we doing with those roots? Just jump in with the keys right there for now. Okay, I'll sign in a second once I get this done. Where's H in respect to those roots? So listen guys, you can always memorize stuff. Please do not forget that. You can, but that's not necessarily the easiest. If we can understand where it's coming from, where is H in respect to my roots? It's using that line of symmetry, so where is it in respect to those roots? It's where? It's in the middle. Mathematically, how do we find the middle? By finding the... Oh, guys. Let's say I gave you the numbers 5, 7, 15, 28, and 32. How would you find the middle of those 5 numbers? You would what? You would average them. Guys, what are we doing with our roots right here? You're just averaging them. Yeah, you can memorize that equation, but also it's in the middle. Mathematically, how do we find the middle? We average them. At some point, you learned the midpoint formula, didn't you? Does that sound familiar?
Yes.
Anybody remember what the midpoint formula was?
Was it X? I don't know if it's the right one. Over.
Because guys, if we're trying to find the midpoint, the middle, what are we really doing? We're finding the average. I don't memorize the midpoint formula. I mean, I know it. I don't think about it that way now. I just think about, hey, what's the average? That's all it is. If you want the middle, you're finding the average. It's in the middle of the root, so just average it. And we're going to play with this some today, but don't forget, if you substitute h in, what are you going to get out? Once you find h in either of those, you substitute h in, what's the output? Okay, right? So if you can find h, and I know this sounds super theoretical, we're going to look at some problems with this later, but if you can substitute h in, what are you going to get out? You're going to get k out, okay? So if you can find what h is, either finding the average of the roots or opposite of b divided by 2a. By the way, remember, you can, one, go back and watch the videos, you can do that, but two, you can actually go back and access the Desmos activity as long as you logged in. You don't need the code. If you log into your Desmos account, and you will actually see your activities there, and you can go back to the forms of quadratic equations activity to help play around these things and see it. The only one of these values that we don't easily see right away is this one. The opposite of b divided by 2a, like it's there. The only reason why we don't see it yet is because you need calculus to understand where that's coming from. Okay? So, when you get a chance to take calculus, you'll learn about something called a derivative, and it'll be like, oh, that's where that's coming from. It blew my mind when I found that out. But, hopefully there's a little bit of a recap. These different forms, right? We got to know these. We got to be able to identify each form. That's those are the foundational pieces. But the whole point, what we're working to today, is being able to graph quadratics by hand using the key features in vertex form, factored form, standard form, and then being able to convert from factored form to standard form. So, one thing I do want to say really quickly as a reminder, I get it, it was the weekend, but if you take, I don't know, 10 to 15 minutes a day, and someone even made a note of this when I asked, hey, what's something you would suggest for those who need a little bit of help? I think that was on week 4 reflection. They're like, hey, I just take like 10 to 15 minutes a day at home, and it really helps me know my stuff, right? So that's something to keep in mind. Just 10 to 15 minutes a day, reviewing the concepts, doing a couple of practice, check your understanding. Really, really, really helpful there. Oh, and don't forget, we moved this thing down into target, right? So creating 2 variable equations in vertex and factored form. We're going to be working on that tomorrow and Wednesday to prepare for that test on Thursday. All right, true to form. So jump in a little bit. So I want to talk about this piece here, and then we're going to get to the pieces that you cut out. So Christine has a standard form. F of x equals 2x squared plus 12x plus 10. And that quadratic equation is in what form? Oh, by the way, this is a slightly modified version of what is actually on page 54. We're just going to talk through this. Yeah, this is out of the book. Slightly modified version of what is on page 54. I might actually print this out for you because I have a copy of this. Not right now, but after, when you get started on the next activity, I'll make copies of this so that you have this explanation because I think it's slightly different. Oh, it's 55, I lied. Sorry for lying to you. No, it's the same principles. So yeah, if you want to, you can just rewrite Kate's equation. I'll explain why in a second, but I use a slightly different equation than the one they have for Kate. So, notice I want y'all to read this. I want y'all to read through this. Take 60 seconds, read through it, and we're going to talk about what is happening in Christine's problem, like what she did, and then we'll talk about it. So actually read through Christine and Kate. Raise your hand quickly once you finish reading it through. It made a little bit of sense. I don't know. Huh? I don't know. Yeah. Yeah, but that's not till next unit. Yeah. But also, when we look at it that way, where does that quadratic form come from? It comes from complete squared, right? Which is a beast to do. So I may look at that to explain it, but when we're just talking about the forms. Yeah. That's a fair point.
It like just occurred to me.
Yes, and I've done that in the past, but I don't usually derive the quadratic formula because it just eats up so much time. If I was teaching out for one, that'd be a different story. Because that's what we're supposed to. If you want, it's right there. Okay, so let's talk about this a little bit. Looking at this, what did Christine do? What did Kate do? What did Christine do? Okay, so how did she find the vertex, right? That's what we want to recognize. And so if you want to label this at the top of your page, or put it in the notes later, that'd be a good idea. So Christine's finding vertex from what? So Christine found vertex from standard form. And how did she do that? Negative b, or opposite of b divided by 2a, because I know it says x equals the opposite of b divided by 2a, but what x value is that actually calculating? Because I wouldn't write x equals, I would actually write something else. It equals what? Right, that's calculating h right here. The opposite of b divided by 2a. And so when she does that, she got what h value? She got negative 3, right? And so all she did was, and one thing that you can do, and I would highly recommend, is label everything. Ax squared plus bx plus c. Every time you write out that equation, it's going to help you remember it, right? That standard form is ax squared plus bx plus c. And so what is a in Christine's equation? Be careful, that a is not 2x squared. A is just the what? A is just 2, right? A equals 2. What does b equal? 12. So remember, the x squared and the x are not a part of a and b. That's just a and b are the coefficients. What are your questions about that calculation of h? Okay, looks like we're good. So what did she do from there? She substituted the value into the function. But why? But why does that give us the y? Like, why is that working? What's going on there? What's implied? An input of h gives me an output of, right? Remember, that's a point. Input of h gives me an output of k. That's it. So she substituted her h in, and when she did that, she got a k out. F of negative 3 equals negative 8. And so there's her vertex. Okay? Now Kate. Kate did something honestly pretty similar. What did Kate do though? She used R1 and R2. And so what did she do with R1 and R2? By the way, why did she get a negative 5 and a negative 1? Because I see x plus 5 and x plus 1. I hear like kind of quiet something, but I don't really hear much. Well, why did she get a negative 5 and a negative 1? She took the, what's the mathematical term for it? It's not really a flip, it's the, starts with an O. Opposite, right? So flip is more like an idea of a reflection on a graph. An opposite would be the opposite sign. Okay? So why did she have to take the opposite? Anyone remember? Why do you have to inverse it? Say that one more time. We're trying to get those zeros, right? Don't forget, like it's not random. There's two ways to see this. One, if I have 0 equals, does anyone remember what really important property I can now use with that factored form? That's actually the opposite of what I want to do. Zero product property. See how I have a product of what? I'm multiplying these things, I got a product of 0. What's the only way to multiply things and get a 0? If you multiply by a 0. That's the only way for this to happen. So either x plus 5 is equal to 0, and or x plus 1 is equal to what? 0. And what would I have to do at this point to solve? Minus 5. Notice how we get the opposite there? Hold on to this, guys, because this is really going to help you next unit. If we start to go ahead and learn, hey, if you have factored form equal to 0, 0 products property, right? The only way to multiply things and get a 0 is if we are multiplying by a 0. So either x plus 5 is equal to 0, or x plus 1 is equal to x plus 5 equals 0, or x plus 1 is equal to 0. And note, you can substitute it in. What's negative 5 plus 5? 0. If I put a positive 5 in here, will that create a 0? No, I need the opposite, so it makes a 0. Right? Don't forget the output for x-intercepts is 0. So, please hold on to that. Anytime it's an x minus r1 or x minus r2, it's got to be the opposite because we want to get that 0. From there, oh, that's completely wrong. We got to fix this. Sorry, I just realized this bottom piece is incorrect. I didn't type this out. I was working with someone, and I don't know how I didn't catch that mistake. But notice h is equal to what? What did she do with those roots again? She found the, starts with an A. She averaged them, right? Isn't h in the middle of my roots? We looked at it graphically earlier. And then, so what did she do from there? F of negative 3. She substituted. Substitute what? H, because if I substitute H in, I get K out. Whew, there we go. So you'll notice there's a standard form here. We shouldn't have a standard form. We should have this factored form. And so what does K end up equaling? Negative 8, right? Multiply it out. There's my K. All right. So she substituted all that in, got K out. So one of the big things, what is similar about these methods? If you substitute H in, what do you get out? You get K out, right? If you substitute H in, you're going to get K out. Now, what I want to challenge you to do at this point is I want you to just take a couple minutes, go up to your vertical surfaces, and I want you to write each of these functions in vertex form. So I want you, we just found our vertex, I want you as a group to go up to your vertical surfaces and write these equations in vertex form. It'll just be a couple minutes. I know a handful of us are still taking notes, but once you finish those notes, get up to your vertical surfaces. Point this out. First off, their vertexes were the same, so what's going to happen with their vertex form? It's going to be the same, right? Now, keep in mind, because this is a mistake that is very common, first off, how hard was it to figure out what A was? Not very hard, because does A change? No, so keep that in mind, right? A does not change. That is a beautiful part of this. So A was 2. Now, I know that there's always confusion about what to write inside of the square. What I need to remind you is, and so Mr. Hobby and I will help y'all, those of y'all who are not done in a second, but one of the first things is, again, the concavity should be super easy to identify, right? Keep that in mind. Then look at the form, because if you have factored form, you're looking at the what? What are these called? So those are called roots, which are parts of your what? The roots are part of which points though? We need to be clear. X-intercepts, right? That y value is 0. So remember, roots tie into your x-intercepts. If you have vertex form, you're looking at your what? Vertex. And if you have standard form, what do you see besides the concavity in standard form? Y-intercept. Guys, looking at it efficiently and quickly and saying, hey, that's y-intercept. My y-intercept is 21. What graph did that go with? I don't remember. Say it louder. C, right? When I look at equation H, immediately I see that graph is concave down, A is -5, and my y-intercept is 21. Instantaneously. Look at the equation, look at the form. And so I do have this up here. I'll write this up in a second so that if you need it, you can do it. One thing I will point out is you already have all of this information for the different forms in your notes. If you want to rewrite it again, that's actually not a bad idea. Every time you rewrite it, it'll help it stick a little bit more because we are going to do a demonstrated understanding by the end of tomorrow with these forms. Hey, Ms. Ember. Gotcha. Thank you. Let's see. What I want to point out really quickly is this. Those of y'all who are done, I want you to move on to page 57, and you have a generic graph in 57. Okay? You have a generic graph in 57, and you have 8 different equations that may go with that graph. If you're not quite done gluing your stuff, finish gluing your stuff, and Mr. Howley and I will help you with this. But I need y'all to do numbers 1 and 2 tonight to help prepare for your demonstrated understanding. Do your check your understanding. But for example, when I look at f1 of x right here, f1 of x is equal to -2 times x plus 1 times x plus 4. Could that equation go with this graph? It matches the what? Concavity matches. Concave, it's concave what? Down. Check. What about could this, based on, what do we see with the 1 and the 4? Those are the roots. Could those roots go with this equation? Notice these roots would become negative, wouldn't they? So this is to help you practice quickly and efficiently identifying, hey, those are just negative roots. So could f1 of x go with that graph? If you are done with gluing, work on this. This is a homework. Make sure you justify yourself. But there's a homework assignment that we'll start by going over tomorrow. We're not going to take a ton of time in class to work on it. But move through those assignments. Make sure you're using this to help you grow and learn.
Oh, do you want to cut this
All right,
out?
y'all figure out which ones to fix.
I don't think so.